have Kristian Seip to give a talk in our cycle of seminars. And as you can see, he will talk about Fourier interpolation with zeros of the Riemann zeta function. Please.
Well, thank you very much, and thank you for the invitation. Very nice to be with you. Unfortunately, I cannot see you, but well, I'm used to this now after having taught for several weeks in this fashion, so I hope it works. So this is some joint work that I did with Andrei Bondarenko and Danilo Radchenko. And as you can see, it deals with the Riemann zeta function. So I think that it could be useful to give you a sort of a, well, let's say a crash course on the very basics of the Riemann zeta function. If you know it, then I hope you just enjoy it, and otherwise I hope that it can be a little bit useful. So, well, this is what I'm planning to say. Some key facts then about zeta, which is what is behind, you could say, this, well, the Fourier duality, which is a main point of this talk, the Fourier duality between the primes and the non-trivial zeros of zeta. And then, well, I will speak about the specific result about the zeros of zeta, but I would like to place this in context by giving some general comments about this general phenomenon of Fourier interpolation, what it is.
Kristian, excuse me, let me interrupt for a second. We are still seeing the first slide. The title slide, the slide with the title.
Well, that's interesting. Okay, how can I do this better? Now you cannot see the second slide?
No, I personally can't. Filippo, do you see the second slide?
No, I can't either.
No,
okay.
No, me neither.
So what do I do then? Wow. Ooh, what do I do? I have no idea. I can move with my arrows. Should I do something else than moving with the arrows?
I don't know why.
No, the arrow is fixed.
So no, you can see nothing.
We just the first screen, the first slide.
If you move on the right, there is a cursor like.
But what do you see now? Do you see anything different from what I showed you?
No, it seems it's okay. Now it's moved. The arrow is moving.
Is it better to? Is this maybe this is better? No.
Yeah, that would be better. This is full screen, but can you scroll the page down?
No, I cannot. So this didn't work. Okay, this I didn't expect. I went into full screen old method. Should I go to something else? A zoom window? No.
Probably you can scroll from the right. Maybe.
Mm-hmm.
In your computer, it scrolls, right?
Yes.
Okay. I don't understand how we see your.
Did you share
the screen?
Did you share the whole that happens on your laptop, or for some reason just when you did the screen sharing, were there various options, or?
There were. Should I go back to that? Maybe.
Or maybe yeah. Maybe you can stop sharing and start sharing
everything if it's possible.
Okay. So what should I do?
Try to share again now the screen.
Yeah. Okay.
Oh, now we can see your arrow for the first time moving.
Oh, you can see the arrow.
Oh, that's right. Try to scroll.
Bring to. No, no, it can't. No, I cannot move the arrow. Come on.
And if you scroll from here,
does it work?
No, now the arrow is frozen again. No, now it moves. Okay.
But we still see only the first page.
Kristian, why don't you try, instead of sharing the file, because I think you shared directly the PDF. You
Yeah.
might try to share your
Screen.
your
Yeah,
screen.
that's what I was suggesting.
Okay. Let's see. I go to the share tray. Could it be this one?
Okay, and now if you put,
Yeah.
I think,
Yes,
on full
right.
screen, it should work.
Right, that's a screen.
Yes, because this
Okay,
is the
Perfect.
screen.
great.
Great.
That's perfect.
Great.
I'm really sorry.
Oh,
Okay.
no problem.
So well,
Please
this is I will only speak about zeta. I will not speak about L functions, so only zeta. Okay, so then we are ready to go, and we start with the zeta function, and I guess you all are familiar with the definition in terms of Dirichlet series, and we have another definition, possible definition in terms of the Euler product. So product over the primes, 1/1 minus p to the minus s. Both of these definitions make sense when the real part of s is larger than 1. And this I say here, and this equality was observed already by and used by Euler. And the interplay between these two definitions, that is what leads to the duality between the primes and the non-trivial zeros of zeta. And that is what I will start by recalling. Okay, so we go first to what we get out of the Euler product. So what we do with the Euler product, that is exactly what relates zeta to the distribution of the primes, or the prime counting function pi of x, which is the number of primes up to x. So what we do is that we take the logarithm of the product, we get the sum, we take the logarithmic derivative, and we get this expression for the logarithmic derivative of zeta, where the coefficients are lambda of n, which is just a computation here with a logarithm, known as the von Mangold function. So this is lambda of n is log p if n is a power over prime and 0 otherwise. And there is a classical formula known as Perron's formula, which is what we get by integrating zeta prime over zeta against x to the s over s along a vertical line to the right of the 1 line. So c here is larger than 1. Then we simply get back the sum of the lambda n's up to x. And then is just a matter of making a partial summation to get an expression for the prime counting function pi of x. It is psi of x over log x, and then we have this integral, and we have an error term which is no worse than of order square root x. So the point here is that as soon as you know psi of x, the Chebyshev function psi of x, you basically know pi of x, the number of primes up to x. So that is what we get out of the Euler product. And then what do we do with the Dirichlet series, this additive definition of zeta? That's where we get the analytic continuation. So one way to get the analytic continuation is by simply writing up zeta in this way, and then you get out the pole at 1, the second term. And you can actually, if you want, continue with this and move to the left and get a meromorphic extension of zeta. But as you probably know, there is another way of doing it, which is to establish the functional equation. So the functional equation, I guess you have seen it, but for what we're doing, it is sort of very basic with the functional equation, and that's why I would like simply to refresh your memory about the functional equation. So if we follow Riemann, what he did, I mean, he actually had two proofs, but we take this one, I guess the best known proof of the functional equation. We start from the definition of the gamma function in this way as an integral from 0 to infinity, x to the s minus 1 against e to the minus x. And if we do this termwise in the additive definition of zeta in the Dirichlet series, we get, oops, now I'm going too fast. So then we get this equality here. So we get zeta times this gamma factor is just the integral from 0 to infinity of a function omega of x, where omega of x is the sum of these Gaussians, e to the minus pi x n squared, which each term here corresponds to the terms of zeta in the Dirichlet series. And then the crux of this is to recognize that we have here a theta series. If we take the sum from minus infinity to infinity, we have, by the Poisson summation formula, we have this functional equation for the function omega of x. And if we go back to the integral and now take advantage of this, splitting the integral into an integral from, well, actually splitting the integral into two pieces, 1, 0 to 1, and then 1 to infinity, we can collect everything in an integral from 1 to infinity, which will look like this. We get out the pole. Actually, we get another pole at 0, and this corresponds to the pole of gamma at 0. And if you take a closer look at the expression that you now got, you see that it is invariant when we shift s to s minus 1, or 1 minus s actually. So this is what this gives you, that this function on the left hand side of the equality is invariant under the transformation s goes to 1 minus s. And what you see immediately from this, well, by this symmetry and the Euler product formula, the zeros of zeta outside of the critical line, real part of s between 0 and 1, are just the negative even integers, what we call the trivial zeros, which you get from the poles of zeta. Of gamma, the poles of gamma. Sorry, I'm pointing it at the wrong place. The poles of gamma. Gamma is here. Okay. So then I have one slide here, which I will come back to. It is sort of a sidestep now, but we will come back to it later. Let me just show you what you get if you now use this functional equation and use the argument principle. You get to count for the number of zeros. Now we know that we have the trivial zeros and all other zeros are in the critical line. And we can count now the number of zeros of zeta up to height t. We call this n of t. And we get a very precise expression for it. As you can see, we have locally a density of zeros. At height t, we have, in a unit interval, we have approximately log t zeros. I mean, this is a very precise version of that statement. And you have some additional terms, each of interest. 7/8 actually is of some interest. And then you have a remainder term, s of t, which is a much studied object, which you can, in a certain sense, view as the imaginary part of the logarithm of zeta on the critical line, or if you like, essentially the argument of zeta on the critical line. As I said, it rests on the argument principle and the functional equation. So this is one thing that we immediately get out of the functional equation. And all terms here, except this mysterious s of t, come from the gamma factor by the use of Stirling's formula. Okay, so this was well, I couldn't resist to say something about s of t because it's such an interesting object. it has been studied a lot, and we still don't know. Well, we are very far from knowing the right order of growth of this function when t goes to infinity. Okay, so now we come back to the connection between zeta zeros and the primes. So I give you what I refer to as the first version of this. So what we have so far are two different ways of expressing the logarithmic derivative of zeta. So zeta prime over zeta. The first thing we did was to use the Euler product to obtain a Dirichlet series for zeta prime over zeta. Secondly, now that we know that zeta has a meromorphic extension, just one pole at 1 and otherwise analytic, and we can show that this is a well, if you disregard the pole, we have an entire function of order 1, and such functions can be represented by Hadamard products. So if you use the Hadamard product instead of the Euler product, you get for the logarithmic derivative the expression that I have put on the right-hand side of this equation. So the left-hand side is what we get from the Euler product, and the right-hand side is what we get from the Hadamard product. So there is a constant there, which comes from the exponential factor in the Hadamard product. Then we have what comes from the pole of zeta, 1 over s minus 1. Then we have a term which comes from the non-trivial zeros of zeta. Rho is a non-trivial zero of zeta, zeros in the critical strip. So we have this term. And then we have a term which corresponds to the trivial zeros. So these are the zeros that come from the gamma factor. So this is then, of course, valid when the real part of S is larger than 1, since we have a Dirichlet series here that to have convergence of that Dirichlet series, we need to require that the real part of S is larger than 1. So this is the basic formula that connects the primes. You can think of this, remember that this is a sum over prime powers, and we should think of this basically as a sum over the primes, because the higher powers don't really play any essential role. So this is, the left-hand side is essentially a sum over the primes, and everything on the right-hand side is understandable, except, of course, the mysterious sum over the zeta zeros. So this is the basic connection between the two things. And one can then try to emphasize this relation in various more or less explicit, to get more explicit information. And the classical approach now is to get from this an expression for this function psi of x that I had in the beginning. So you get this from the formula on the previous slide. Well, I think maybe, did I say, sorry, yeah. So you get it by counter integration. Okay, so you remember what we did on the first slide. We had Parent's formula, so that gave us the left-hand side. And if we plug the expression that we now have on the right-hand side, I'm referring now to what we have here with the sum with what we get from the pole and the zeros. If you plug that into Parent's formula and use counter integration, you get the expression on the right-hand side here, which is first the term x, which comes from the pole. Then I chopped off the sum because it's convenient to have a finite sum. So we only take the zeros up to height t. That gives us x to the rho over rho. And then you have a term coming from the trivial zeros, which is not so important. And then you have an error term, which comes from what we did by here cutting the sum at height t. So this is the basic formula that gives you the relation between psi of x and the non-trivial zeros of zeta. So you get then the usual expression for pi of x by a partial summation, which is this integral, this logarithmic integral 0 to x dy over log y plus a remainder term, which you can express in terms of the non-trivial zeros of rho, and you can write it in the way I did here. You have here x to the beta in the sum, where beta denotes the real part. I put it up here. So rho is beta plus I gamma. So we sum up to height t, so the imaginary parts are all less than t, and we have here x to the real part of the zero. So you see the significance of zeros being on, well, if you expect them to be on the real line, then on the critical line, you see how important that is for the size of this term, because a single zero off the line would make this remainder term correspondingly larger. So this remainder term, it looks like this, and then of course I guess I already more or less said that if all the zeros are on the critical line, then you get this remainder term as small as you can hope for. Basically, it would then be of order square root x log x. Okay, so then there is now other ways you can get information out of this relation that I had between the two ways of writing the logarithmic derivative. So this is known as the Riemann-Weil explicit formula. So one does more or less the same thing, but instead of taking the specific function that we did in Perron's formula, which was x to the s over s, we plug in any function, any test function, which we call h of z. So we take any reasonable analytic function. It is analytic in a domain which contains the critical strip. It satisfies a reasonable growth estimate. And then if we then play this basically the same game, we get a sum of the values of h at the non-trivial zeros of zeta. Well, actually, to make it look as a Fourier analytic duality relation, I now mapped the critical line to the real line so that it really looks Fourier analytic. Okay, so that's why I subtracted a half and divided by I to send the critical line to the real line. Okay, so you get the values of h summed over the non-trivial zeros on one side. On the other side, you get two terms which come from the pole, and actually I made it symmetric so that you have one term corresponding to the pole of zeta and another term corresponding to the at the symmetric point corresponding to the pole of gamma at 0. And then you get two additional terms. You get, well, when you make it into this, write it in this symmetric way, you get an integral of your function against the logarithmic derivative of the gamma factor, which is what you have here. And then you get a sum over prime powers again. Lambda of n is supported on the prime powers. Again, you should think of this as a sum over the primes. So this is the duality between the primes and the zeta zeros expressed as a Fourier duality relation. Yeah, and of course, here I have, as you see, defined the Fourier transform with a 2 pi in the exponent. So this is a Riemann-Weil formula, and so it is, as I said it, and I wrote it here, that what we do is we replace x to the s over s by this function h, and then to get this symmetric form of the explicit formula, we use the symmetry which is expressed by the functional equation. So that was, I guess, what I wanted to say as an introduction about the duality between zeta zeros and the primes. So now we will move in the direction of another Fourier duality relation. Again, a Fourier duality relation that will involve the non-trivial zero sum zeta. I will, as I did already, I will use this usual standard notation for the zeros, but I will do something a little bit non-standard. I will account for multiplicities, possible multiplicities. Well, people don't believe that there are multiple zeros, but let's keep that possibility open. So m of rho is the possible multiplicity of a zeta zero, and I will give you a statement which is sort of analogous to Riemann-Weil, and I would like to work with a space of functions which is more or less the same kind of functions that you plug into Riemann-Weil. But let me make it precise. I look at functions f. I call this set of functions h1, functions that are analytic in this strip, which you can think of as the critical strip plus epsilon. And I require a certain integrability condition. It's a technical thing. We couldn't allow functions to grow too slow, to decay too slowly in this formula. And then we will also need to speak about functions that behave very nicely. So we will say that the function which decays in the way I've written here. So along any horizontal line, it decays in this way for any power L here. L can be anything. So it's sort of the same thing as you see in the definition of a Schwarz function. Right. So then I give you our theorem on the next slide, I think. Yeah, and I state the result for even functions because the statement is slightly more convenient. So this slide is our theorem. I'm afraid it's a bit long, but I hope I can explain what's going on here. So perhaps I should say that, well, f now is, so this f is as a function in this space h1. And I consider values of this function inside of, well, what corresponds to the critical strip. Again, I repeat that because I want to look at it as a Fourier duality, I sent the critical line to the real line. So that's why, but I think of it all the way as, all the time as the critical strip. That's where we are. Okay, so this function f in h1 can be represented at every point as a sum of two terms. The first term are the values of the Fourier transform at the points log n over 4 pi for all positive integers from 1 to infinity. Un of z, that is a sequence of nice rapidly decaying functions, and they are even and of course entire functions. So then there is a second term which is over the zeta zeros. Again, we have this possibility of multiple zeros. That's why I need to have a sum that takes that into account. So for every zero, If the multiplicity is m of rho, we need to take all derivatives up to m of rho minus 1. Again, we have a nice basis functions corresponding to each of the points zeros rho and multiplicity j. And for some technical reason, I have to take a little bit care when I have to be a little bit careful with the summation. So I couldn't sum it in an arbitrary way, but it converges in an appropriate sense. So we can represent every function in this way as an interpolation formula, where you have on one side the values of the Fourier transform at log n over 4 pi, and on the other side you have values of the function along with its derivatives, if needed, at the zeros of zeta. And there is another important thing to say about this, and that is that these functions un and v rho j, they have the following interpolatory properties. So basically what I'm saying here is that in an appropriate sense, the system of functions is complete and minimal. Okay, so each one of them takes a value 1 at the point and is 0 everywhere else, including at the other side of the Fourier transform. So, so this is the theorem. And it is, I would like now, before I say more about the theorem, I would like to make a relation between Riemann-Weil and this kind of, I will refer to, well, I should say that I will refer to this, to a result like this as Fourier interpolation. So it means that I have a function with two sequences, one on each side of the Fourier transform, one in the space and one in the on the frequency side, and when I can represent a function in terms of an interpolation formula involving values at these two sequences of respectively the function and the Fourier transform, I will say that we have Fourier interpolation. So what is the relation here? Well, let's say first that both of these formulas, they rely very crucially on the functional equation. But there is a principal distinction here, and that is that the deduction of Riemann-Weil, it starts from the Euler product, while the Fourier interpolation formula that we had on the previous slide, it is tied to the Dirichlet series representation of zeta of s. But what I find quite striking is that you could say that the two formulas express respectively a multiplicative, that is the Euler product version, and an additive duality relation between the zeta zeros and a certain distinguished sequence of integers. So you have two different kinds of Fourier duality involving the zeta zeros. One multiplicative in nature and another one additive in nature. That is a way to look at these two different duality relations. You might also notice that the sequence of integers involved in the Riemann-Weil formula is a very thin subsequence of the corresponding sequence appearing in the Fourier interpolation formula. Maybe I should go back to it to make it clear. Here, you sum over all integers and you have log n over 4 pi. In the Riemann-Weil formula, you are summing over prime powers, and you take, in that case, log n over 2 pi. So it's sort of like the difference between the two is that one is the square root of the other. So it's, I mean, that's roughly speaking in terms of density. So it's a much thinner sequence than you have in the Riemann that you have in the Riemann-Weil formula. Yeah, that's what I write here. At the bottom of the page, that it's basically the square root of the integers. What I write here. There is another thing to say about the relation between these two formulas, and that is that once you have this basis representation that I showed to you, we may think of Riemann-Weil as the representation of a certain linear, distinguished linear functional in terms that, I mean, this is we can think of what I wrote here. Well, I don't know if this works, but I hope you can see that I point on the screen. So the functional that I've written up here, we can think of as a functional that acts on functions in our space H1. So what the Riemann-Weil formula can be seen as is the representation of this functional with respect to the basis that we have. And in some miraculous way, you see that when you look at this particular functional, in fact, what remains is a very thin, I mean, only a very thin sequence of basis functions, in fact, give a contribution to this formula, which is a quite remarkable case, a fact, I would say. So this is so you could say that what I have done so far is, on the one hand, to say that these two formulas are respectively a multiplicative and an additive Fourier duality. And then I'm now saying that you can also think of Riemann-Weil as sort of sitting inside of this additive relation by viewing it as a representation of this distinguished functional. Okay, so that's about this specific situation. And now I would like to say something about what started this activity. Where does it come from, this business of Fourier interpolation? So there is a remarkable theorem of Radchenko and Vyazovska published last year, which is as follows. So we are now in a similar situation, but we now look at a sequence which is symmetric. So it means that we have square root n on both sides of the Fourier transform. Again, for convenience, we stick to even functions, and we only now consider Schwarz functions. So f is a Schwarz function on the real on R, taking real values, and then the result is that functions in the Schwarz space, or even Schwarz functions, can be represented in terms of a Fourier interpolation basis. So we can have basis functions an, and then we have the Fourier transform of an. So it's symmetric and also in this way. And then we can express f in terms of the values of the function at square root n and the Fourier transform of the function at square root n in this way. And again, these basis functions have nice interpolation properties. It's a little bit more subtle than we had in our case because, well, we have we still have they are complete and minimal, but you see that there is a subtlety with the values of the a-n's and a-hat-n's at the squares of the integers. So at the squares, they are actually and I should say also at zero, specifically at the point 0. So at the point 0, they in fact take the value -1 when for squares of the integers. Well, I should say, well, one of them is -1 and the other one is 1. So these are the interpolation properties of these functions. And the thing that I just said has a very beautiful interpretation, because what you get if you now plug in x equals 0 in this formula, So then you see from what I wrote here that only squares survive, and then the square root n becomes n, and what comes out then is in fact the Poisson summation formula. So the Poisson summation formula sort of sits inside of this formula of Radchenko and Wiatrowska. So again, now we have a curious analogy between the Poisson summation and Riemann-Weil formulas. So you can view both of them as representing certain distinguished linear functionals in terms of a Fourier interpolation basis. And you can also think of these two formulas as, well, they owe their existence and importance to an inherent algebraic structure, which in the first case you could say is additive. I mean, here we have periodicity, which is behind the Poisson summation formula. And in the case of the Riemann-Weil formula, it is the multiplicative structure which is behind the formula. So this is one way to look at the analogy between Poisson summation and the Riemann-Weil formula. Right. So since we had this trouble in the beginning, I'm not sure how much time I have. Could it be something like 15 minutes more, or?
Yes, please.
Yeah. Okay. Okay. So what will I do now in the remainder of the talk? I will mainly provide motivation for our approach, why we did what we did, and try to place it in context by saying some general things about Fourier interpolation. And I will ignore a lot of stuff. There is a very interesting history behind all this, which comes from the problem of optimal sphere packing in dimensions 8 and 24. What we rely on is the same things as in the Radchenko-Wiatrowska work. We rely on weakly holomorphic modular forms for the theta group. But as you probably understand, I will have no time to say anything about that. And then there is a lot of technicalities here, which I will not say much about. We had to work quite hard to get to the critical strip plus epsilon. So I cannot say much about that. But I would like to just mention one result which comes out of these technicalities, and that is that we are able to get a fairly precise result about which functions can be represented in terms of this interpolation basis of Radchenko and Wiatrowska. So, I mean, it's more or less clear that you need something more than only f and f hat being in L1. So the result we have is that you can do this Fourier interpolation if f and f hat, well, they should be in L1, that is more or less clear. And we add a little bit more, that the derivatives of f and f hat are integrable against these weights. So it seems to me that it is, well, I would be surprised if you can do it much better than this. It seems to be we are getting pretty close to what is possible to do with this. Okay, so but that's a technical thing. So let's go to let me say some general things about Fourier interpolation. So when we did this work, we saw that there was an approach that worked, and then we wanted to sort of see if this is what we're doing is sort of what you, I mean, it is it just ad hoc, or is it somehow the right thing to do? And we did some, we tried to prove some general theorems to say more or less that this is this approach is sort of there is a general phenomenon here which explains why this approach works. And now I'm coming back sort of to things I said in the beginning about functional equation for the zeta function. So it's a similar thing that you will see now. So what we are doing is we are assuming that any reasonable function can be expressed as we have seen as a sum over the values of the function at a certain sequence lambda, and we have the Fourier transform over a certain sequence lambda star, and we have some nice basis functions g lambda and h lambda star. So I'm not discussing now. So all these, let's say, all functions are reasonable. We have conversions and so on, and we also require that there is a dual representation. Okay, so also f hat should be expressible in the same way. Then you see that what I'm basically doing is I'm taking the Fourier transform of this relation, and I get a similar thing for the Fourier transform. These are, I think, are quite reasonable things to require. But I don't assume anything about minimality, which is what we had in our theorem. I don't assume that we have complete that we have minimality of this representation. This plays no role in the arguments. Okay, so what is it I want to say? What I want to say is that under suitable assumptions as I described above, the two general Dirichlet series, I mean, these are general. I mean, the frequencies here are well, let's say basically anything. In the previous case, we had log n, right? So we have two general Dirichlet series associated with. Well, now I write the thing for lambda star. Okay, so I can do similar things for lambda, but now I write the Dirichlet series for lambda star. So I take the positive frequencies in one series, and I take the negative frequencies in another series, and the coefficients will be the basis functions of the corresponding basis functions of the basis. So the statement is that these two Dirichlet series admit meromorphic extension to C for every x. For all the, the coefficients will vary with x because these are functions. So for every x, these two Dirichlet series admit meromorphic extension. And what is very crucial, with simple poles at x and at the points of the dual sequence. So the duality can be expressed in terms of these Dirichlet series and it's and so in terms of their meromorphic extension and the poles of the meromorphic extension. So it's something very similar to what we saw with Zeta. There are two things to say. I didn't write explicitly that E plus is this guy and E minus is this guy. There is a small technical issue which is behind that, but basically what you have is that these two Dirichlet series are intertwined by a functional equation, and then, as I said, by duality, well, I'm not sure I said it, but I'm saying it, by duality you have an analogous result when you replace, you just switch the roles of lambda and lambda star. So this is this is the kind of duality, another way of expressing this duality in more analytic terms. And then conversely, Dirichlet series kernels with such properties generate by counter integration. It is the usual counter integration that one does in analytic number theory. So you get the Fourier interpolation formula whenever you have this situation which I have now described. So this is really the general setup for Fourier interpolation. And I said it and I repeat it that you should notice the resemblance with the first version of the explicit formula that I explained in the beginning of the talk. It's really the same kind of thing that you're seeing. I have a PhD student, Kulikov, who looked at what kind of relation there has to be between the two sequences. And what he found is that there is a general density that you need to require from the two sequences. So I call that the joint density of lambda and lambda star. Okay, so this is something quite familiar with in Fourier analysis that you measure. So we have functions that are essentially supported on the space side on an interval, and on the Fourier side it is essentially located to an interval from minus. So you have minus t to t on the space side and minus w on the Fourier side. Okay, so now we count the number of points in each of these intervals. We call the counting function n lambda of t and n lambda star of w. Remember that we have two different sequences, one on the Fourier side, one on the space side, and one on the Fourier side. So we count the number of points in such an interval. And what Kulikov proved is that there is a very precise joint density. Well, you should count now. You should add the number of zeros that you have on these two intervals, and this sum of the number of points should exceed 4wt minus a small term, and this holds whenever w and t are, let's say, larger than or equal to 1. Well, there are some technical assumptions here, but we can basically ignore that. Whenever we have a Fourier interpolation formula, we need to have this density relation between the two sequences. And this is a result which you, well, I should say that this relies very much on some beautiful estimates of area Israel for the so-called, well, it's actually for the, if you're familiar with the Proles-Freudel wave functions, which are the functions that you get when you study, well, the time frequency localization operator for in this situation. So this is a quite non-trivial result. And what is satisfactory to see is that if you look at the examples that we have so far, Radchenko, Biatsovska, well, then I wrote down for you what the counting functions are. It's very easy to see. That's 2t squared and 2w squared for these two intervals. And so you see that you have t squared plus w squared larger than or equal to 2wt. I mean, you don't have 4 because you are only looking at even functions. So it should, so you get only half. That's why it's 2 and not 4. If you go to the Zeta case, what is quite satisfactory to see, I'm sorry, it's maybe too much text here, but you should just go down here and see that what you get is precisely as a lower bound, you get the leading term in the Riemann-Weil formula. So you see it's pretty sharp. I mean, it's clear that he hit the right that he hit the right density. Yeah, I think since time is running, maybe I should skip this slide. It's just some general things about crystalline measures, so it's not really so essential for what we're doing. I'm just relating what we do to let's say, ongoing research on crystalline measures. Now, let me just say a few words about our Dirichlet series kernels. I mean, you saw on the previous slide that that behind the scene there are certain Dirichlet series, and I call them Dirichlet series kernels. Okay, so the core ingredient in our construction is a Dirichlet series of the kind that you saw in the general context before. So it is now, since we are back in the Zeta situation, we have n to the minus w over 2. You can think of this w over 2 instead of just w as corresponding to what I said before, that we look at this sequence which is much which is much more dense than we have in the Riemann-Weil formula. So that explains the square root that you have. And then you have basis, well, you have coefficients that depend on the second variable s. So you have a function of two variables, w and s, coefficients depending on s, and then you have w in the exponent here. So this beta n, they are Fourier coefficients of a certain, well, a two-periodic analytic function on the upper half plane. And it is related through a Mellin transform to the functions that you got, that you have in the Radchenko and Vyazovska basis. So it's our beta n's are strongly linked to the bn's that come from Radchenko and Vyazovska. So yes, well, maybe that's enough to say. I mean, there are some small things here that the bn's are not quite the an's, but it is the Fourier invariant part of an. But it's the same thing basically. This Dirichlet series converges absolutely in a half plane, depending on S, and has a meromorphic extension, just as Zeta does, with simple poles at 1 S and 1 minus S. And what is the really crucial point, why Zeta now suddenly shows up? So why should Zeta show up? Well, there is a small miracle happening here, and that is that this series, which I wrote up here, it is really tuned well with Zeta. So basically, the basic point is that this series satisfies, in an appropriate sense, the same functional equation as Zeta does. So this is what I'm saying now. So this dw of s is related to Zeta in the following precise way. The function that you get by multiplying and dividing by Zeta, well, you multiply Zeta of s and you divide by Zeta of w. This function satisfies a functional equation of the form that you wish to have. I mean, this is what I said about this general situation. You want to have functional equations for your Dirichlet series kernels. So thanks to the relation between the two objects here, this Dirichlet series dw of s and Zeta of s, they essentially satisfy the same functional equation. You get this nice functional equation, which is really what we need to prove the result. Once you have that, well, then you do the usual things. You integrate, you use contour integration, and you can then use that. Well, look at what we have here. We have in the denominator Zeta, so it means that you pick up the zeros. The zeros of Zeta will then correspond, will actually give you then, when you do contour integration, you get the values of the function that you're integrating against when you move around, let's say, a rectangle or so. So this is the kernel that is behind the basis function. So let's see now. So again, but in the game is similar as the game we played in the very beginning of the talk. You look at this and integrals like this in two different ways. If you do it directly, you get and plug in the Dirichlet series, you get the values of the Fourier transform. And when you go to the complex, when you do a complex contour integration, you use the residue theorem and you get the values of the function at the points. So that's how you get the duality. You have, again, you look at an object like this in two different ways and compute it in two different ways. Well, there is actually an abundance of Fourier interpolation formulas around this, let's say, this kernel that I wrote up for you, because there are plenty of L functions and Dirichlet series that satisfy functional equations. And whenever you have a functional equation with a gamma factor, you should expect to have formulas like what we have. So there is really an abundance of such formulas. This is I just wanted to say that. So what this can be summarized in the following way. So this function dw of s that I wrote down for you, it generates really an abundance of Fourier interpolation bases. Yeah, and you could say that this situation relies on the special multiplicative structure which is inherent in this setting. So it's really a special setting that we can do things like this. Yeah, and here I just say that we could use other gamma factors, but let's not say anything more about that. I want to finish by saying a few words about related work, because there has been a lot of activity in this general setting of Fourier interpolation. So Ramos and Sousa had the idea that one could extend Radchenko-Jaczowska to other sequences, and they specifically were wondering about what happens if you take n instead of as Radchenko and Jaczowska had. They had the square roots of the integers, right? So then alpha and beta would be a half. So they were wondering if you could do the same if you have that alpha plus beta is strictly less than 1. Okay, so you have really well, you have in some sense more points than I mean, you should have infinite. You should expect sort of infinite excess in this situation. This was proved by this is now a theorem by Nazarov and Sodin, and they in fact established a result like this for more general sequences, but still sequences that in some sense are below the critical density in terms of the Kulikov theorem that I showed to you before. So the Kulikov theorem shows you where exactly the critical density is, and what Nazarov-Sodin did was basically to show that whenever you have a sequence which is strictly, two sequences which are strictly together, the joint density is strictly larger than the critical one, and the sequences are sufficiently regular, roughly speaking in the same way as here, but they allow more general sequences, then we have a uniqueness result. Here, Ramos and Sousa required uniqueness. Now, Kulikov joined this team, and now they have a theorem saying that in fact, in this situation, we have Fourier interpolation. We wouldn't have minimality anymore because we have infinite excess, but we do have Fourier interpolation. So Fourier interpolation, really, there is an abundance of Fourier interpolation formulas, and you can think of this in some sense as what happens here in the work I described here above, Nazarov-Sodin and Kulikov-Nazarov-Sodin, is in some sense to connect the two cases I have spoken about, square root n, which is Radchenko-Jaczowska, and the Zeta of S case, which is our result. So in terms of densities, you could say that they sort of bridge between these two cases. I mean, if you look at sequences like this, n to the alpha and to the beta with this restriction, you are sort of in between in terms of densities, right? And we are sort of representing an endpoint case here in terms of densities. But we had in our result minimal Fourier interpolation, right? So these systems were minimal. And this seems to be quite, I mean, this seems to rely on certain miracles, if you like. I mean, it really relies on this things which I didn't speak about modular forms and multiplicative functions. So a question you could ask is whether it's possible to obtain this kind of minimality in other situations than square root n and this zeta of S case. Would be very interesting to know. And of course, I guess that there are other things also to explore about these spaces, which I think are quite fascinating. So, but I think my time is out probably, so I should stop. So thank you very much for your attention.
Thank you very much, Kristian. Okay, very nice talk. Thank you. I want to ask if there are any questions.
I had a curiosity. I wanted to ask if there was any connection with these quasi-crystals and crystalline measures, and I already know there is because you skipped the slide.
Yeah, there is. I mean, all these bases they automatically give you. I mean, in a suitable sense. I mean, some people require certain technical things about these crystalline measures, so that technically it's not the same. But I think in principle, it's you always get that out of formulas like this. So it sort of contributes to, well, let's say the establishing the abundance of such measures. Yeah.
Okay.
Yeah.
Ask just
are there any questions?
Yeah, Marco.
Go ahead.
No, so, Kristian, can you just briefly comment on the modular forms? Just do.
How it's done?
Yeah, or how they enter the picture. Let's say just.
Yeah. I mean, it's a very beautiful observation here. That I mean, I'm no expert in this, so I really rely a lot on in our team. It's Rashenko who is the expert in this field. Now I wish I had a blackboard to write on, but these functions. Where is let's start with, well, I can go back to can you see still the screen?
Sure, yes.
Yeah, so if we go back to this function that I had, this bn of s.
Yes.
Okay, so this is defined. I mean, you can define it as a Mellin transform of this other function bn, but then you could ask where does this bn come from? Well, they come from, so you integrate, so you get them from certain well, functions gn, which are modular forms. So you have, well, I should have had something to write on. You get them by integrating certain modular forms against a very specific kernel. So in the case of the bn's, you integrate these gn's, which I would have to say a lot to explain exactly what they are, but there are let's say a theta function involved, and there are certain other modular objects involved in that. You integrate that against, in the case of the bn's, against a complex Gaussian. So it's e to the I pi x squared z, and you integrate that along a, well, you can decide, I guess, your curve in the upper half plane, but they do it along a semicircle from -1 to 1. And in the case of the beta ends, you have a different kernel than the Gaussian. And the reason that they connect so well is that when you have the Gaussian and you take a Mellin transform, you get the gamma function, right? When you have, it's the same phenomenon as you have in the zeta function. So that's why the two things connect so nicely. You had in the first case the Gaussian, the same phenomenon as in the zeta case, and that is sort of explains why it's so natural to go from from the basis that they had to a basis related to Zeta. I'm sorry that I'm not able to explain so much more about this setup because it's quite complicated with I mean these modular functions. It's a little bit tricky, and you really need to write up formulas, I think, to say anything more useful. Sorry for that.
Okay, no, thanks. It helps when one reads.
Yeah.
Thank you.
Are there other questions? Well, I have one here. This beta n coefficient is just in this line, the definition of the kernel.
Yeah.
How explicit are they? This is very specific.
How explicit?
I mean, this current.
Yeah.
Yes.
It's how should I say? It's I mean these are very interesting. I mean you couldn't really put your hands on them, but you can say quite a bit about their analytic properties. So and you can you can probably say more than what has been said so far. I mean, but you have to work quite hard. I mean, to get in, let's say, explicit. But I can say things like the beta n's. If you go in the vertical direction, they decay like e to the minus some constant square root t. Things like that. We can say very precise things about partial sums of these beta n's. About the bn's, one can say fairly precise results about the zeros, where they are. So, but I think there are, if people are interested, there are certain things to explore about these functions. I mean, they're from a time frequency point of view, they are very interesting objects because they are sort of, they are very interesting related to the uncertainty principle, but because in some sense they are, how should I say, they are in some sense extremal, because if you add one point to these sequences, everything collapses. It's very sensitive, right? If you add, you have these two sequences. You have a function that vanishes on everywhere except at one point. But if you require it to vanish at that point, you are not able to cook up such a function. So it's really, they are really extremal in a certain sense from the let's say the uncertainty principle point of view. So I think they are really fascinating objects.
Oh, okay. Because I assume from what you said from this formula on that you actually need quite a bit of information on beta n's.
Well, that to have this analytic information is a good part of our work, which I didn't say anything about. So you really need to have precise estimates to be able to work with them. So this we have, but it's hard to get your hands put your hands on a specific BN. I mean, you have.
Go ahead. Sorry. Okay. Well, I had other question about the H1 space, but I guess I can look at the notes later. I mean, the slides later. Are there other questions? Otherwise, I think we can thank Kristian again for the very interesting and illuminating talk.
Thank you very much, Kristian.
Thank you.
Thank you very much.
And
absolutely.
Okay.
And, okay.
Now we go for a beer.